So let's talk about what a power series is. A power series is of the form, it looks something like this. It's the sum from n equals 0 to infinity, c sub n times x to the power of n. And if we were to expand that, we're going to get c sub 0. Actually, let me make that look like two separate things. C sub 0. Because if I plug in 0 for the exponent, of course, that becomes 1. And then plus c sub 1 times x to the power of 1 plus c sub 2 x squared plus c sub 3 x cubed plus dot 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 plus c sub n x to the n plus dot dot dot, where x is a variable and the c sub n's, however that's supposed to be written, are constants called the coefficients of the series. So if we go back up to here for a moment, where we're looking at 1 over 1 minus x is 1 plus x squared plus x cubed and so forth. This is a power series, okay? This is your basic foundational one that you're going to need to memorize because we're going to use it over and over again. Later, not so much in this section, I think, but in the next section quite a bit. We're going to be using it to build different types of power series. So this is a foundational one that you're going to want to remember. But here, the coefficients are all one. Happens to be that all the C's in this case are all exactly the same. They're all one. That's not always going to. It's not going to happen very often, but probably never again. Well, I shouldn't say never again, but they're not always going to be the same. So keep that straight. So we're dealing with, a series where, adding a bunch of terms together, and these terms now have a variable in them. In the stuff we were dealing with before power series, we were just adding together a bunch of numbers. And sometimes the pattern of the numbers got complicated, but here we're just dealing with a bunch of numbers. I'm sorry, we're not just dealing with a bunch of numbers. We're dealing with a bunch of variable expressions. So this is why we're taking it to the next level. I don't want you to become panicked by this leveling up. I want to give you a little bit of an analogy from an earlier portion of mathematics where things at one time seemed a little bit more complicated and then quickly became something that was understandable. So let me take a break from this discussion for just a moment and start talking about this. Back in an earlier math class, fifth or sixth, seventh grade, you would be given, an equation, something like this, a linear equation. And then, your teacher would say, well, after you've learned all your order of operations and all that, then X's were the inputs and Y's were the outputs. He or she would give you a bunch of values, and then you would do a bunch of calculating, and then you would get a collection of points. And then you would learn that this graph, when you lined up those points, was something like this. Went through at the y-intercept of 1 and had a slope of 2, and the points lined up nicely. And then eventually, through all of your different experiences, you stop thinking or needing to think about lines in terms of some concrete values, and you learned the general, slope intercept form for the equation of a line, good old y equals mx plus b. Now, when you first learned, y equals 2x plus 1 in similar examples, you didn't know much about it. You couldn't recognize what was happening here. You couldn't recognize that that the two, when you very first time you were learning this, that the 2 meant the line was going up from left to right because it was positive, and the 1 told you that it crossed the y axis just a little bit above the x axis, 1 unit specifically above the x axis. But eventually, when you got down to this form here, you knew that if m was positive, the line was going up from left to right. You didn't have to see it anymore. Or if m was negative, it was going down from left to right. Or if m was 0, it was horizontal. And you knew what b told you. You knew that b told you where the graph crossed the y-axis, positive above the x-axis, negative below the x-axis, but that's where it crossed the y-axis. So you were leveling up from here to here, becoming better at understanding the relationships without having to see concrete numbers. That's what we're doing in this example here, or at this time here. You know that, or you should know, that this is a convergent geometric series, because the common ratio is 2/3 and it has a magnitude less than 1. And you can calculate what it converges to. All we're doing now is we're now thinking about, and this is a simplistic form of what we're doing because we're going to be doing more sophisticated examples. We're just taking this and saying, all right, let's forget about the fact that that was 2/3. Let's just make it x. And let's talk about what happens now that x is our quantity that we're multiplying by each time instead of 2/3. How does that change the problem? Okay. Well, again, we know if the magnitude of x is less than 1, we know the series will converge, and we know we'll converge to the first term divided by 1 minus common ratio. We can start talking about it more abstractly than we used to be able to talk about it, because now we're getting more familiar with these types of series. This is essentially what we're doing with a power series. We're not using a series of constants anymore, which is what this is over here. We now have a series of variable terms. It's a very simplistic example. But we have a series of variable terms that are changing in a predictable way, usually, and we're going to be able to say more about it. We're going to want to know when it converges, what values that we're going to plug in here that's going to make it converge, what values are going to make it diverge. When it converges, we'll be able to find out what it converges to, sometimes, not very often, and other things that we're going to want to be concerned with for this. So that's our goal. Our goal is to get to a point where we're now seeing variable expressions being added together in a certain pattern and identifying those as a power series. And then we're going to take the power series and we're going to flip it around, and we're going to start with functions and want to know what kind of power series represents that function. But we'll get to that stuff later. So the way I want you to start thinking about this now is, for each value of x, if we go back up to our power series, c sub n x to the n, starting from n equals 0 to infinity. Okay, c sub 0, whoops, the auto feature turned that c into something that I didn't want. Anyways, c sub 0 plus c sub 1 x plus c sub 2 x squared and c sub 3 x cubed. Get a little sloppy here. I apologize for that. All the way out to c sub n x to the n plus dot dot dot. Okay, I want you to think about this now a little bit differently. Okay, we want to think about this as a function. Okay, a power series defines a function f of x is equal to this sum from n equals 0 to infinity c sub n x to the power of n, whose domain is the set of all x for which the series converges. So I think this is a pretty cool feature here. So we're going to start thinking not just in terms of sums, not in terms of sums of constants or sums of numbers as we were doing in previous examples. We have the sums of variable quantities going on forever, and they represent functions, at least a function on the intervals for the values of x for which the series converges. And we're actually going to be reversing this. We're going to be asking the question later for a certain function, like the sine function. Is there a power series that represents that function? And if so, how do we find that? So this is going to be, the bigger picture idea that we go on as we go on further. Now, this is a rather specific series here. This one here, being centered at the origin. We're going to allow ourselves to shift this series and not always be centered at the origin. You guys know about shifting functions like we used to back in the day. So we're going to do this in a more general way. So a more general power series is the sum from n equals 0 to infinity c sub n times x minus a to the power of n, which of course is going to be c sub 0 plus x minus a. Whoops, that's not true. Forgot c sub 1 on there. Trying to go too fast. C sub 1 times x minus a plus c sub 2 times x minus a quantity squared plus, and I'm going to run out of space here, so I'm not going to put the third term down. I'm going to jump to the nth term, c sub n times x minus a to the nth plus dot, dot, dot. This is called a power series, or I'll just put is a power series centered at A. Now, you may have noticed something here that typically we're going to, let's look, we get C sub 0 here. How do we get C sub 0 by itself? Well, that means I'm going to have x minus a. This means that x minus a to the power of 0 has to be equal to 1. Okay. Now we want that to be true, and it makes sense. But if you're paying close enough attention, what happens when x equals a? Now, if x equals a, then x minus a to the power of 0, shouldn't that be 0 to the power of 0? And we're calling that 1? Didn't we say that was an indeterminate form back in L'Hopital's rule section? Absolutely we did, but you know what mathematicians do? They break their own rules when it serves their purpose. So we are going to allow, for this example, x minus a to the power of 0 to be equal to 1 even at x equals a, so that the pattern holds. Mathematicians are going to break the rule here that 0 to the 0 should be considered an indeterminate form for this pattern here, because the pattern holds and it looks nice. So we're going to let the pattern hold and let it keep looking nice. I keep pausing the video and doing some things. I hope the pauses are working the way they're supposed to. Let me switch colors here. Let's get an example going here. So example number 1. Find the values of x for which the power series is convergent. So we're asking the same question here. Power series that we have before, when does it converge? Does it converge? Is it convergent? So we're still concerned about convergence here, as we have been many times over. So it's negative 1 to the power of n plus 1 times the quantity 2 to the n x to the n over n times 3 to the n. So you may start wondering, how are we going to figure out what values make this convergent? Well, you could start plugging in values of x and do like a guess and check method, but you might be there a while. You might notice a pattern eventually, but that's not the point. We definitely don't want to start doing guessing and checking. There's nothing wrong with plugging in some values just to see the behavior of the function for certain specific values of x. But in general, that's not the technique we're going to use. Not too long ago, I told you we have a new sledgehammer in our arsenal of ways of showing series are convergent. That's the ratio test. So this is what we're going to be using here. We're going to be using the ratio test a lot in this section and the subsequent sections here. So how do we use the ratio test? Remember, the ratio test takes a look at the limit as n approaches infinity of the absolute value of the n plus first term divided by the nth term. Now, since we're using absolute value and our series has this expression in it, okay, that expression in it, of course, makes the series alternate signs. But since the absolute value is going to be in our limit expression, the signs are going to all become positive. So I'm not going to write the -1 to the power of n plus 1. It's just not needed here. So I'm going to take the 2 to the n and make it 2 to the n plus 1 times x to the n plus 1. Divide that by the quantity n plus 1. Be sure to use parentheses here. Times 3 to the n plus 1. And then we're supposed to divide by the nth term, but I'm going to multiply by the reciprocal just out of, skipping a math step. I don't want to have to write out the fraction of the fractions like this, or separately. I want to write it like this. All right, so we have this. Now, the nice thing about all of this is we're going to get a lot of things canceling. For instance, 3 to the n cancels with 3 to the n plus 1, leaving a 3. 2 to the n cancels with 2 to the n plus 1, leaving a 2 up over here. Similarly, x to the n cancels with x to the n plus 1, leaving an x in the numerator over here. Fortunately, I can't cancel anything between the n and the n plus 1. So this becomes the limit as n approaches infinity. I can't drop the absolute value yet, even though I didn't use that -1 to the n plus 1 term way back up from the original expression. I still don't know the sign of x. X could be negative, and that could cause the quantity to become negative, and I need these absolute values still to be there. So what's left? I got 2 in the numerator. I have an n in the numerator and an x. In the denominator, I got a 3 and the quantity n plus 1, like this. Now, as n goes to infinity, we should understand that the n and the n plus 1, all that goes to 1. So essentially, this thing is going to go to the ratio of the coefficients. So this becomes 2/3. Can't forget that x there. And I need that absolute value to be on x. So this limit as n goes to infinity is 2/3 times the absolute value of x. What does that mean? Well, if you think back to the ratio test, remember the ratio test in the conclusions converges when that limit is less than 1. Okay, so we need 2/3 times the absolute value of x to be less than 1 for the series to converge. Well, okay, that means the absolute value of x has to be less than 3/2, which means, well, I'm going to go through this in a minute. I'm sort of pausing in my head. I want to explain this now. You may recall, you may not recall from an earlier math class. That means that -3/2 is going to be less than x, which is going to be less than 3/2. So those are the values of x for which the series converges. Now remember, the ratio test tells us that the series diverges if the limit is greater than 1. So we get 2/3 times the absolute value of x greater than 1. Actually, let me go back and write this. This is going to be the converge part. Converges. And then for diverges, we have this. So that means the absolute value of x is going to be greater than 3/2. Now, from an earlier math class, you may remember that means that x is going to be greater than 3/2, or x is going to be less than -3/2. Again, I'll talk a little bit about that in a moment. This is diverges. One other thing from the ratio test, remember the ratio test fails if the limit is 1. And so, if 2/3 times the absolute value of x equals 1, this is where the test fails. So that means absolute value of x is going to be 3/2, which means that x is going to be plus or minus 3/2. Those endpoints that we had in those up here in the earlier examples. So I don't know what happens here. It means I got to use a different test. All right. I didn't want that to come up. How do I get rid of this? All right. So I have to look at these points separately. If x is equal to 3/2, well, now I'm going to have to go back and look at the, I'm sorry, not the limit, at least not yet. I'm going to have to look at the sum from n equals 1 to infinity, -1 to the power of n plus 1, 2 to the n. Now x is 3/2 to the power of n, and that's going to be divided by n times 3 to the n. I got to see if this converges or diverges. Now we're back to the old previous stuff that we used to use. All right, let's see. Is this a type of series? Well, it is alternating. But let me see if I can simplify it before I go through all that algorithm, looking at types and the nth term test and all that stuff, because this thing looks a little bit complicated here. Notice we got this little 3/2 to the n. That's 3 to the n over 2 to the n. Well, the over 2 to the n is going to cancel with this part here, and the 3 to the n is going to cancel with this. A lot of stuff cancels there. So this nicely looks like the sum from n equals 1 to infinity, -1 to the n plus 1 over n. Do you recognize that? This is the alternating harmonic series, or one version of it. And therefore, or you may remember which converges. This thing doesn't want to drag anymore. Did I run out of... Okay, which converges? Thought I ran out of virtual graph paper there. All right, we also have to test what happens if x is -3/2. And if x is -3/2, I get the sum from n equals 1 to infinity, this -1 to the n plus 1, 2 to the n, -3/2 to the n over n times 3 to the n. Again, I got to see if this converges. I got to go through the algorithm, but let's do a little bit of algebra first. And I just keep messing everything up. Let's see. Getting used to these new tools. I'm in my expression here, I still got 3 to the n and 2 to the n, but I also have a -1 to the n. So a lot of things are going to cancel here, but there's still something left, unlike before. So I still have -1 to the n plus 1, that was out in front. The 3 to the n over 3 to the n is going to cancel, 2 to the n over 2 to the n is going to cancel, but I still got a -1 to the n over n. What is that? What is that? Well, -1 to the n plus 1, this one's going to be negative sometimes, and then this one's going to be negative sometimes. But no, they're off by 1 in the numerator here, or I'm sorry, in the exponent here. So when this one's even, this one's odd. And when this one's even, this one's odd. So one of them is always going to be negative, and one of them is always going to be positive, which means that this thing is always going to have a -1 in the numerator over n, which is just the opposite of the, make that a little more pronounced, the opposite of the harmonic series. And the harmonic series diverges, so taking the opposite is still going to diverge anyways. So let's write that down. This is the opposite of the harmonic series, which diverges so the power series way at the top that we were dealing with converges if negative 3 halves is less than x, because remember it did not converge at negative 3 halves, which is less than or equal to 3 halves. Okay. Now remember that the ratio test gives us absolutely convergent. Okay. So that means the series is absolutely convergent from negative 3 halves less than x less than or equal to 3 halves. Or if you prefer the interval notation, you can do open or parenthesis negative 3 halves, comma 3 halves with a bracket. It means the same thing. All right, I'm going to break the video up, so I'm going to stop here and start a new video for the rest of it.